if we have an integral, so is it an indefinite or is it a definite?
These are definite integrals. Yeah.
So if it equals to 0, can't you say it has to be split up into two parts that are both, that if they're evaluated that equal to 0 would have to have an antiderivative?
Well, I don't see why. I mean, how would you how do you get the big F? You know.
But there, if you don't have a big F, you couldn't have it equal to 0.
Why?
Because it'd be undefined. Because you couldn't take an integral.
Well, I think you can. I think there are cases where the integral works out to 0, and yet
The function itself is undefined.
yeah. I mean, it can be such that there exists a loop that integrates to 0, but not all loops integrate to 0, and that can happen. See, the point here is that this is just a straight formula for F. And now you can judge, and by the way, this is something you saw in physics.
I saw in physics.
Believe it or not. So like, well, before I get sidetracked into physics, let me explain to you why how do I explain that? I have to give an argument, all right? So it can argue that f prime of zeta rather exists, and in fact f prime of zeta is equal to f of zeta. Which is, I mean, that's what we need for this, what I wrote in purple to gel, right? But also notice that it's really just the fundamental theorem of calculus part 1 in our current vernacular as well. I mean, it's now
So argue f prime exists, and if f prime exists, f prime, say
I mean, that's what I need. I need that, you know.
Wait, well, it wouldn't matter if f prime exists because you couldn't say that its antiderivative exists.
I need big F prime to be equal to little f, otherwise I have not succeeded in constructing big F, right? I mean.
Oh, yes.
So, have you ever seen this construction of the potential from integration in Calc 3?
The potential?
I mean, this is the
Talking about physics or Calc 3?
Well, it should be covered in Calc 3. I have to kind of go back here for a second. But in physics, you know, we have the electric force, right? Is equal to minus the gradient of the voltage function, right? So, if you want to write a formula for the voltage at R, right? You can say, well, that's minus the integral from the origin to R, right? And I should put an E here if I'm going to put a V there. Because the gradient, E dot D, we'll usually use R there.
Yeah. I've seen this before.
So when you differentiate this, you get that.
Oh, yeah, So that's what we're doing over here. So we'd have to
It's an
find.
obvious, yeah.
It's like,
Maybe I should show you an example. Let's see here. How about we look at the function, the force. We'll keep it real simple, like 3 comma y. Pretty simple force field, right?
mm-hmm.
I want to say that that's the gradient of, some potential. Now, of course, you could just calculate the potential directly by guessing.
Mm-hmm.
But in the current way of thinking, we could also do this way. F of xy is the integral from, now you pick your origin for the potential energy we're going to be. How about the origin?
Yeah.
Easy. 0, 0. 2 xy. And then we'll do f. I'll use bars. X bar, y bar, dot, dr. Let's see here. So my claim is that it doesn't matter. It doesn't matter which path I use. This is a path-independent force field.
Mm-hmm.
The work done by that force field around any path is equal. All right?
Mm-hmm.
So let's see here. So I might as well use the path. I might as well just use, gamma of t equal to, tx, ty, 0 less than or equal to t less than or equal to 1. That's a nice parameterization.
Mm-hmm.
Right, so then I've got integral from 0 to 1. I have to take f, evaluate at that, right? So that's 3, and then y is ty.
Mm-hmm.
And derivative of that, well, that's xy. X and y are fixed here. In the integration, x and y are fixed.
For the r, for r hat?
Mm-hmm. What I'm saying is x and y are fixed here, so this integration is over the curve that goes from 0, 0 to xy, which has parameterization, this. I can draw a picture of it. So here's a point in the middle.
So when you're evaluating from sort of the f hat, you're saying that it's
3 is 3, y, I have to plug in y bar, which is,
so why wouldn't it be 3t?
because 3 is a constant, and when I evaluate the constant 3 at tx,
Zero.
it's still 3.
Okay.
But the derivative, dr dt, is xy, and then I still got my dt. So what do I got? I've got integral 0, 1 of 3x plus 3t squared y squared dt.
And we integrate of t,
Mm-hmm.
so we get a 3xt. Alright.
Good. I was like, I didn't remember hitting record. It was terrifying for a second there.
The 3xt,
3xt, right?
and then 3 over 2 t2,
Yeah, 3ft, yeah.
Squared,
But
y
3ft
squared.
squared, y squared.
and then evaluate it from 0 to 1 of t, so just give you 3x plus 3 half y squared.
That's the potential for that. You can take the gradient
Mhm.
and get that.
you take the gradient of that to get back.
Gradient of this is 3 comma 3 halves times 2y. Okay. Partial, like, gradient of f is partial x, partial y here.
Okay.
You know, 2 dimensions. And,
Wait, so I don't. Shouldn't you be able to get rid of that 3 then? Because you get y back. So when you do the partial x, you get 3. When you do the partial y, you get 0 plus.
oh, I shouldn't have a 3 there.
Yeah.
I don't know if I got a 3. I shouldn't have had a 3 here.
Yeah. Okay.
Sorry about that. Yeah. You're correct. Thank you, sir.
Okay. Yeah.
I can't do math.
Okay. So we go back over here. We're doing the same thing. So what we'd have to do is set f equal to something already on that derivative.
Well, I mean, you don't want to actually. We don't have a specific f, right? This is an arbitrary f. So like.
Well, it's just.
This is just an example.
Yeah.
The question is why? Why does this construction work? You know.
Well, because essentially you're just taking the derivative of both things, and the derivative cancel out. Because f is equal to, so I mean, one sec. You're looking for the existence of an f given f prime. And so if you integrate f prime, oh wait, no, if you take the derivative of f and it gives you f prime, that means it exists without having to find an antiderivative.
I mean,
so
right. I mean, I'll write it out. To prove that this works in general, we have to issue the partial derivative of x of the integral from whatever point we have, you know. And it doesn't have to be 0, 0. Let's use an arbitrary point, x naught, y naught, right? To xy of, f dot dr. We have to show that that's equal to f. Excuse me, that's equal to. I need to call it. We call this a. I'm going to suppose f, not a vector, f is equal to ab, okay? So like, I need this, right? And I also need this and that. If I have this and that, then those two things together imply that the gradient of little f is equal to AB. Where I'm defining little f according to, the integral of the given half independent vector. So the question is, why is, and so like, to really do that, the argument is something like this. You have to start at your point, x naught, y naught. You got this target point over here, x, right? X comma y. Are we going to need to, you need to move to be okay? Can you get out? Move.
Oh, good.
You can just pull onto the lawn, it's fine.
No, I wouldn't do this. Principle.
Eh. All right, so we need this. I'm trying to remember. Calc 3 that like I feel like I'm about 80% correct on, and there's just something, there's like some small nuance that I found one year and I taught it really well and then I lost it again. So I'm going to give you my 80% solution right now, okay? And so the point is we're assuming f is path independent. So we imagine we're working on 1, all right? And so basically you can just go, okay, well I'm going to take, I'm starting my origin, and then I can approach this point horizontally, right?
Yeah.
And so, the point is I'm trying to calculate the partial derivative with respect to x, you know? And I suppose what that means is I should consider, you know, holding y fixed but varying x a little bit. So like this is the right kind of path to do that. Now, so when I actually integrate, let me call this part C1, and I'll call this CX. All right, so I've got, you know, I'll need to just focus on the integral over, you know, integral from x naught to y naught all the way up to xy of f dot dr is equal to the integral over c1 of f dot dr plus the integral over cx. And the cx is the interesting part, okay? So cx, it's going from like,
We're not assuming it's straight.
cx I'm assuming is straight.
Okay.
Cx is horizontal, so y is fixed. Y is held constant. But we're gonna, you know, the x is in something like so x minus delta, I suppose, to x. And then I need to do, so here's the thing, is dr dt, what is it? It's 1, 0.
Yeah.
So when I take dr dt dot f, and f is ab, I just pick up a. All right? A evaluated where? Well, a evaluated at t comma y, all right, dt.
So you get wait, is the inverse, but the inverse from x to x.
Right.
So what do you get? How do you evaluate at x?
Oh, that's, like I said, that's the thing I'm getting.
Well, you said t is in between x and.
Tell you what, so this is this is the 80% thing I was talking about. I think if I just say that this goes from like, you know, 0 to, well, that's the thing, it's like, I don't know. I want something independent of x there, you know?
Why? Independent? Oh.
Yeah, so,
Yeah, that way you get like x.
yeah, let me just suppose it's like x naught plus 1 or whatever, you know? Now, obviously, that's making an assumption about the size of the universe in which I'm making this argument. But you see, you could, for a given thing, you could put something here that would be independent of x and somehow based on how the shape is. And, you know, as long as this is an open set, you can finagle the curve around to get like horizontal line segment approaching, going through that point, actually, either side too, like, you know. Because it's open, like there's no edge to the domain. Okay, so all of this, so when you okay, so then to calculate the partial derivative with respect to x, what do? We differentiate this with respect to x holding y fixed, right? So if you differentiate this with respect to holding y fixed, what happens? Well, this piece has no, this has no x dependence. It's got a y dependence, right? But no x dependence, so that drops out. What happens when you differentiate this with respect to x holding y fixed? Well, this, if you take the x of it, what do you get? Well, you get a of x comma y. By fundamental theorem of calculus part 1, if we differentiate an integral with variable bounds with respect to the bound, we evaluate the integrand at the bound and we get that. And so that's part 1. Now obviously my analysis on the x naught plus 1 piece is pretty sketchy, right? I mean that could be improved. But essentially the same argument.
And partial y, but partial y looks a little better just because you have straight up y.
Right, so for that one, you use a different path.
Mm-hmm.
You do something like, you know, like that.
Okay.
So that this one has parameterization like x comma, you know, t. Where, you know, you go from whatever to y. And so you can get this. But now, I'm sorry I'm not doing it justice today. I've made this apology before. If I teach Calculus 3 again, I will fix it. I'm pretty sure. Or I'll have the good sense to not try to prove it and just tell them, oh, it's true. Look at it, look. But there's nothing intrinsically two-dimensional about these arguments. In fact, they're easily generalized to 3. You can still draw the pictures. You just kind of, for the x derivative, you go, oh, and then have a little, just going along the x direction, right? For the y, just go along the y direction, just go along the z direction at the end of your path. Mm-hmm. And so if you understand this carefully, it's not at all a jump to imagine making the same construction in the algebra.
Yeah, you just find the AXY.
Right, you take your path up to close to the point and then just approach along one of the coordinate directions at the end.
Yeah.
And so that's what I'm describing here on equation 150. Well, 148, so I'm like, define f of zeta as integral from zeta naught to zeta of f d eta. Zetas and etas and zetas in my mind. Anyway, I say, following the usual argument, consider a path from zeta naught to zeta, which is along the vj direction near zeta. Using this path, you can derive that partial xj is f star vj.
Which means that you can find the inadditive root.
Right, and then so that means that partial x1 is f times v1, which is f, right? Which then means that partial xj is f times we see equation 151 there.
Yeah.
So that shows that f satisfies the ACR equations and more than that df d zeta, big F d zeta is equal to f. So in short, the construction of potentials still works in the natural interpretation over A calculus. But I will freely admit that this is something that is not always taught in Calculus 3 in the depth that it should be, because this goes with the discussion of conservative vector fields, which a lot of times gets kind of shortchanged because we get out of time towards the end of the semester and we just spend too much time doing partial derivatives and integrating and such.
Oh, no, but I got the example, the next example,
Good.
and so I get how you constructed it.
So then I next talk a little bit about differential forms over in algebra.
Oh yeah.
So say it's like exact if it's the differential of something else. It's closed if it's exterior derivative is 0. And I define the exterior derivative just by like taking the exterior derivative of each component. Like I'm working with algebra valued forms here. So just let me be less esoteric and just give you like an example. So here's an example. You could have, alpha equal to y dx plus jz dy plus j squared x dx, right? So this would be a one form on H3, let's say. Right. I keep using H3 for you. I think it's because I've gotten tired of using hyperbolic numbers, and it's like, I'm using 3 hyperbolic numbers this time. I'll be different. But anyway, so if I take the exterior derivative, my definition sense basically just says you differentiate. It basically ignore the algebra element, just kind of right along. Of course, that's 0, right? And so what we get here is d alpha is minus dx wedge dy. I just flipped it around for fun. Plus j times. Oh, fine. I'll put a minus here too. Why not? Minus j dy wedge dz. I don't know why.
Yeah, but you end up getting a 2 form.
But yeah, there you go. So the exterior derivative of a 2 form, the 1 form is a 2 form. But notice that this is a algebra valued 1 form. Because it's got like j's and j squareds. So algebra value 1 form. This is an algebra value 2 form as well. So a little bit different. Although we did look at matrix valued forms in exterior in differential geometry, so maybe it's not so out there. Okay. And theorem 10.10, if I've got a function on a simply connected subset of A and it's continuously differentiable in the real Fréchet sense, the A-valued 1 form f star d zeta is exact if and only if f is A-differentiable. So what does it mean for f star d zeta to be exact? If this exact means that this is the differential of some other thing, right?
Big F.
Right. Or big F. Okay, fine. Yeah. That's true if and only if I say f is A-differentiable, right?
Yeah.
Given the presuppositions of the theorem. Now, let's see here. So let's see if we can think through. It's been a while since I looked at the proof, so I'm kind of, I might get in trouble here. I'm not looking at the proof just yet. Let's see, one of these directions has got to be easy.
Didn't we just prove A if f is a differential? No, we didn't prove that. We proved that if there exists a D, if there exists an F on U. Oh wait, from the theorem we can state that, no, that's complex, right? That if f is differentiable once it's differentiable n times, it's only complex numbers.
And so the assumption is, we're assuming here that U is simply connected and F is continuously differentiable.
is different, if big F exists, doesn't, if, does that only work in complex, the Cauchy integral theorem? I thought we proved that for.
Yeah, I
Didn't we say something about that in the
yeah,
general
we can't.
sense?
Right, I don't think we can. I mean, okay. So let's see if we can get. Let's suppose this is true, okay?
Yeah.
And we want to show f as adifferentiable, right?
Yeah, because we're going out.
So we want to check df of v star w, right?
Mm-hmm.
Now df I can write because I'm assuming f is continuously differential. So it's for shape, it's derivative, df exists, right? But I also know that this is equal to d of, what was it, f star d zeta, right? Oh, excuse me. No, I don't get to say that. Oh, I don't get to say that. I don't know. I'm starting with f.
Little f?
Yeah, I mean, I need to. I need to get an f star d zeta to say anything, you know. Man, I'm gonna have to look at my notes. I'm gonna have to. I mean, I'm
Well, dv.
I bet I'll. Apparently, this is not easy.
df v star. Wait, can't you say df v star w? And then if you have df v star w, you can say df of. I don't know. I feel like it's going over df. Can you rewrite as a sum? Of the parts?
So, all right. The way I do this, so this is f is continuously differentiable on simply connected view. This means that Poincaré's lemma is at play. Poincaré's lemma says that closed implies exact. So we can get that there exists a big F if we can show that this is closed. What does it mean for that to be closed?
A loop? What's the definition of closure?
Okay, so let's,
Not
I guess what I'm saying is suppose, I just flipped the sides again, sorry. Suppose F is adifferentiable, right?
Mm-hmm.
If f star d zeta is closed on a simply connected subset, that implies that f star d zeta is exact. And to say it's exact,
Just say it's differential.
no, that means that there exists f such that f star d zeta is df. So all we need to do is prove that for this part of the proof, we just need to prove that f star d zeta closed it is closed, all right? And what that means is that d, the exterior derivative of f star d zeta, is 0, right? So it suffices to prove that. Now what is df here, by the way?
D little f.
Yeah, d little f is equal to what it is it's v1 df1 plus v2 df2 and so forth. Vn dfn. I'm expanding the basis v1 through vn. You know.
Have you seen Mom?
I have.
Where is she?
Where is mom?
I don't think she.
What's it worth to you?
I don't think you know.
See, like I said, the oldest two. She went to pick up Isaac, Daniel. Oh. All right, so I'm gonna run the space here. So I do some calculations leading up to this calculation. All right, so like to summarize, what we're going to see is that we get df is equal to f prime of zeta star d zeta for an a-differentiable function. So d of f star d zeta, it ends up being, you know, f prime of zeta star d zeta wedge d zeta. Which then I also I show that d zeta wedge d zeta is 0. Yeah. So we can break it up into two lemmas. We need to show that d zeta wedge d zeta is 0, and we need to show that df is in fact f prime of z d star d zeta.
Well, that's only to go one direction.
Yeah, that's exactly for the one direction. As much as I try not to bring one direction into things.
They're like old.
I know. So the danger of running into their fans is somewhat slim these days.
I dated girls very much into them.
I'm sorry. Let's see here. So the d zeta wedge d zeta, let's deal with that. Right, so that's the sum I equals 1 to n of vi dxi, okay? Wedged with the sum j equals 1 to n of vj dxj. And so that's the sum over I comma j of vi, and the way this works is you have to multiply times vj dxi wedge dxj. Now we are assuming we're working with a commutative algebra. That was stated at the start of the section. So this is equal to 0. And the reason for that is this is symmetric in I and j, whereas this is anti-symmetric in I and j. So if you contract a symmetric against an anti-symmetric, you get 0. I proved this in equation 152 by taking the sum over an I and j and breaking it into some I less than j, and then some j greater than I, and then relabeling the sums and getting a minus from, because like when you relabel sums, you flip the wedge product and get a minus, but the other one you flip and you don't get a minus. So you end up with being able to cast the part of the integral that has I less than j as minus the same integral with the j less than I terms, gives you the same integral but minus, so they cancel
So
out.
when they're equal to each other, they equal to 0, and then when they're unequal to each other, they have opposite signs.
Yeah,
Got it.
but this is just like standard tensor calculus stuff. So that's why d zeta wedge d zeta is 0. The question still remains, why is df equal to f prime star d zeta? Now this right here obviously does not assume a differentiability of f. But this does. And so can I erase? Alright, so let me do that.
Now we're on part 2.
Yeah, I'm working on why is this true.
Mm-hmm.
So, okay. So df is like partial f, partial x1, dx1, yeah. Partial f, partial x2, dx2, plus plus partial f, partial xn, dxn. Okay, great. Now, if this is a differentiable, then I can take all of these glorious partial derivatives and reduce them to the derivative with respect to the identity element. So, so just for the sake of making this not too obnoxious, assume that the identity is the first basis element, right? So then I have partial f, partial x1, dx1, plus partial f, partial x1, times v2, dx2, partial f, partial x1, times vn, dxn, right? So you notice that you've got, but remember partial f, partial x1 is literally the derivative anyway, so that is factored out, f prime of zeta. These are all that. Times what? Times, well, dx1 plus v2 dx2 plus vn dxn. What is that though? That. Well, that's straight up d zeta.
Yeah.
So there you go. F prime of zeta, d zeta. So, and the A differentiability was mission critical there because without it I couldn't have converted all those partial derivatives to derivative with respect to the first, right? And I'm pretty sure that
Yeah, because if it's not a differentiable, we don't have that.
right.
That lot rule.
Exactly. And I'm relatively certain. I haven't investigated this. I could be wrong. I'll just say it that way. But I have a strong suspicion that you could do like partial f, partial zeta d zeta, star d zeta, plus partial f, partial, and I could be wrong here. Star d zeta bar 2, you know. Maybe. Big maybe. With the Wertinger calculus, you know. It's just for an a-differentiable function, these guys all vanish, you know.
Was this one going left, like proving the
Yeah,
okay.
Yeah, now we gotta go the other direction. Yeah. So can I, well, I'll like Can I erase or?
Yeah, I got all of it. Okay, so now we're going. So now we don't, so all we know is that df, or big D, big F is equal to little f star d zeta.
Yeah, F star. You say that. We know, suppose there exists big F from E to A such that. Now we want to.
For A is differential.
Why is it, right? A differential.
Can we just say, because you can split it up? Oh, wait, no, we suppose that because A was differential, we can split it up. Well, we know d zeta is equal to dx1 plus b2 x2, which would give us an algebra, right? We just work backwards.
We what?
Because on the way forward, we said that.
I'm not saying you're wrong, I didn't quite follow.
On the forward proof, we said that that d zeta was equal to dx1 plus b2 dx2 plus da 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 vn dxn.
Oh,
If we just say that straight up, we can just work backwards, right?
so you're just saying like,
Quite literally work backwards.
it's just like, what is that? That's
Yeah,
F1 V1 FN VN
yeah,
star like V1 DX1.
yep.
So yeah, I mean it's a mess.
If you start multiplying everything across, you'd have. No, that would be squared, right? No, that wouldn't work.
Now, are we getting? Oh, now we. Well, what the? I hope he doesn't bend it. I told them to suck the water out of it with their squirt guns. He's like,
I'm glad I was seeing this kid.
whatever. No, oh, I do think one of the things that I'm not taking advantage of here is that we're given F is a differential. Like that's kind of hidden here in the terminology, but we're assuming that this is an exact form, but that's with respect to A calculus, and that implicitly means that F is itself a differentiable function. Which means we could try to use that to somehow, I mean, so the question is how, I mean, there's clearly some relation between partial derivatives of F, big F, and multiplications of like little f times, you know. What happens if we look at like, oh, can we differentiate this and learn something?
Again, like you like differentiate another time. Well, let me look.
Oh, but I don't know that. Well, I know that f is.
No, we don't know that f is a little f is a differential. We can't
Yeah.
can't assume that.
Well, it's continuously differentiable in a real Frechet sense. So I can differentiate it. I just don't know that it's like df exists, but I don't know that. Let me just write things down. So d of df, right,
Mm-hmm.
is d of f star d zeta, right?
Mm-hmm.
Right. So this is 0, because the d squared is 0. And this is df
0.
starting zeta. Now that
Oh, because the left one.
well, you're right, it has to be equal to 0.
No, I was talking about dd zeta, but it's not distributive since it's.
But yeah, that's essentially, I mean, you can think of it that way. There is a product rule we've derived here and so forth. But this, of course, is, as you know, partial f partial x1. Now, I'm not assuming a differentiability here. I'm just writing out the real, this is using real differentiability. I'm not sure this is going to help us either, Roderick. I'm just trying something. All right?
Okay. Wait, isn't.
I mean, this should really be, I should probably write this as a wedge. Do more.
Wait, and then if you write. No, and then write d zeta as the thing, dx1 plus v2 dx that, and then if you wedge on everything starts going, a lot of things start going to 0.
Yeah, but I mean, true. It's not going to 0. I need to obtain relations between various partial derivatives. So like, if v1 is the identity, right?
Wait, can you pull out dx as a match coefficients? Partial f of partial x1 wedge v1.
So v1 is the identity. So like, yeah, what's the dx1 wedge dx2, right?
Yeah.
What goes there?
Just partial f, partial x1.
Yeah, partial f, partial x1. That's from, but times v2, right?
Yeah.
But then this one, which so that's minus, because I have to flip.
Yeah, I could do it. Just partial f, partial x2, nothing.
Hey, that's what we want.
Huh?
Well, this is 0, right?
Yeah.
So, of course, the next thing is like, you know. So there you get partial f, partial x1. v3 minus partial f, partial x3. This is great, because what we want is that partial f, partial xj is equal to partial f, partial x1 times vj. Those are the Cauchy-Riemann equations.
Okay.
So if this is equal to 0, these are all independent, right? The only way that this 2 form can be 0 is if all of its components are separately 0.
Yeah, which they are, because that's equal to.
Yeah, we can see it just from looking at dx1 wedge. But there's tons more, right?
Yeah.
Like, it's kind of fun. Like, what do you get from dxj wedge dxk, where those are not equal, right?
Yeah.
If you think about the coefficient of that, you got what? You got like your partial
fx1.
yeah, partial fxj times vk, right?
Yeah.
Minus
partial k.
Mm-hmm. That
Yeah.
that's the coefficient of like dxj wedge dxk.
Okay.
That vanishing, well, those symmetric Cauchy-Riemann equations we talked about the other day.
Yeah.
So they're all in there.
Is that if we pull out a Cauchy-Riemann equation, does that prove differentiability then?
Yes, because a differentiability is equivalent to
Oh yeah, I remember. Yeah.
real differentiability paired with solution of the Cauchy-Riemann equations.
Is that what you said in your paper?
That was one of our equivalent characterizations of a
No, I'm talking about as your proof. The algorithm.
Oh, that's a good question. I was deep enough into this when I wrote this, I probably didn't write much. Wow,
What's up?
that is not how I did it in the paper at all.
Is this way nicer or worse?
It's both better and worse. It's better in the sense that it actually, you know, I just think it's a cool calculation. But what I did in the paper was I was like, so I use big F equal to phi in the paper,
Mm-hmm.
and so I'm like, okay, so F prime is phi prime, that's equal to little f, right?
Yes.
But that means that f is equal to partial x of phi, x1. So if I calculate partial j of f, it's partial j of partial x1 of phi. Then I can flip and because phi is a differentiable, I get, you know, since phi is a differentiable, I can rewrite that as and then just oh, and then that's partial f partial x1 times vj when you undo it. And so we have this,
Also the kosher one.
yeah. So I did it a sneakier way, but I actually really like the way we did it today also. Although, anyway. Yeah. Oh. Now, I showed you Cauchy's